Hello everyone, welcome to my channel. I'm Min. In today's video, I would like you to imagine a material with a self-healing ability like a human skin. It can repair itself whenever it gets cracked or damaged. That means you don't have to pay a lot of money on repairs, which could save you tons of money in the long run. Sounds cool, right? And if you don't know what I'm talking about, let's take a look at this video first.
This is a strip of self-healing polymer. That means I can slice it into two pieces and then with the application of gentle pressure, push the two pieces together and it will become once again one single piece.
The material you just saw in the video is called self-healing polymer. In today's video, I'll explain how it works and explore some of its real-world application using fundamental concept of polymer science. And trust me, it's much simpler than you might think. So let's get started, okay?
Can polymers heal themselves? Discover the science of self-healing materials.
The term self-healing in polymers was first introduced by Malinsky and his colleagues in the early 1970s. In their pioneering study on polyvinyl acetate, they created cracks in polymer samples and observed how the material recovers strength after being left at elevated temperatures. As the temperature approached the class transition temperature, polymer chains became bubble and diffused across the crack interface. This molecular interdiffusion gradually reconnected the material, leading to partial recovery of mechanical strength. For decades, self-healing polymers rely mainly on chain diffusion and usually require heating. A major breakthrough came in 2001 when White and co-workers developed the first autonomic self-healing polymers capable of repairing cracks at room temperature without external intervention. The system used microcapsules filled with dicyclone benzadiene monomers dispersed in a polymer matrix together with a catalyst. When a crack formed, the microcapsule ruptured and released DCBD into the damaged area. Contact with the catalyst triggered polymerization, forming a new polymer network that sealed the crack and restored strength. This became the first well-known extrinsic self-healing system, one of the two main categories of self-healing polymers. Although this approach can effectively repair damage, the healing process is usually limited because the healing agent is consumed after use. To overcome this limitation, researchers develop intrinsic self-healing polymers. Unlike extrinsic system, the polymer network itself contains reversible interactions that allow repeated healing cycles. But how does a polymer actually heal itself? The first step is chain interdiffusion. Polymer chains from both sides of a crack diffuse across the interface, so the chains became increasingly entangled. The second step is bond rearrangement. Dynamic bonds with the polymer network continuously reform, allowing the material to rebuild its molecular structure after damage. Several types of reversible interactions can drive this healing process. Hydrogen bonding is one of the most widely studied mechanisms. Hydrogen bonds can dissociate under stress and rapidly reform once the damaged surfaces are brought together. In 2017, researchers showed that combining hydrogen bonds with metal ligand coordination could significantly enhance self-healing performance. The combination improved both mechanical strength and healing efficiency, resulting in highly durable self-healing material. 2 years later, hydrogen bonds were combined with ionic interaction. Working together, these interactions will form strong yet reversible connections that enhance both strength and healing performance. Another important strategy uses dynamic covalent bonds, including diazotar reactions, disulfide exchange, and imine bonds. These reversible bonds provide greater mechanical strength while still enabling self-healing. The healing process can be accelerated by external stimulants. Heating increasing polymer chain mobility. UV light activates dynamic bonds, and mechanical force can trigger bond exchange reactions. Together, these promote faster and more efficient healing. A major challenge is balancing healing and strength. Materials that heal quickly are often mechanically weaker, while stronger materials tend to heal more slowly. Today, self-healing polymers are being explored in a wide range of advanced technologies. One promising application is lithium metal batteries. As lithium repeatedly expands and contracts during cycling, cracks can form within the solid electrolyte. These defects gradually degrade battery performance and shorten battery life. In 2022, researchers developed a self-healing sulfide solid electrolyte using dynamic hydrogen bonds. The material could autonomously repair lithium plating-induced cracks and maintain stable contact. This significantly improves cycling stability, retaining more than 19% capacity after 140 cycles. Another promising application is flexible electronics. Flexible photodetectors are widely used in wearable devices and electronic skin. However, repeated deformation can create cracks that decrease performance and eventually lead to device failure. To address this challenge, researchers incorporated graphene and black forest nanosheets into a self-healing ionic polymer. The nanosheets enhance light absorption, while the polymer matrix provided flexibility and self-healing capacity. The resulting photodetector recover its photoresponse after 30 healing cycles, remain stable after 500 days of storage, and continue operating under strengths of up to 100%. So let's quickly recap. Self-healing polymers are materials that can restore their functionality after damage. They are classified into two categories: extrinsic system, which use embedded healing agents, and intrinsic system that rely on dynamic molecular interactions. Today, these materials are finding applications in electronics, energy storage, healthcare, and many other advanced technologies. I hope this video helped you understand the science behind the self-healing polymers, and thank you for watching. If you enjoyed this video, don't forget to like, subscribe, and leave the comments below. See you in the next video. Bye bye.